Hello AP Physics 1 students. Let's get started in your problem set with numbers 7 and 8. So pause the video, try to do as much as you can in both problems 7 and 8, then come back to see how I solve it. Okay, so we're given a photon, we're given the frequency, and a photon is this bundle of light energy, imagining light to be a particle, it'll have some particle properties. And the first part we want to do is find its energy, so I just want to do E photon equals HF. Now, I'm always going to write E photon. The book doesn't always write E photon, just writes E equals HF. But if I write E photon, I'd like you to write E photon as well, because like I said, one of the major hurdles in this topic is knowing if we're talking about an actual physical particle with mass or this particle of light. And so this is an equation that only deals with light. We're going to write E photon. The problem didn't say what units to put your answer in, so you got your pick. You can use the value of H in 6.63, that's going to be in joules, so you get this value here, or you use the 4.14 value in electron volts, that's going to be this value, and neither one is preferable to the other, because it doesn't say which one to do. Letter B, want to find momentum. Okay, now that's a bit of a weird thing, right? Because what's our usual equation for momentum? That's P equals mv. And what's the mass of a photon? That's 0, right? So it seems like the photon shouldn't have any momentum at all. And yet, remember, this is what Compton figured out. When he's shooting light at electrons, the electrons been scattering off as if they've been hit by an actual object. And since there was a transfer of momentum, the momentum had to have come from the photon. And he worked backwards and figured out the momentum of the photon was based on its wavelength. So here's the equation we use. Lambda equals h over p. Rearrange it for p the momentum, h over lambda. And now, you have to put in your values. But wait a second, you're not given lambda, you're given the frequency, right? So you have to use c equals f lambda, which I'm just going to put right in here into the equation. It's lambda equals c over f, so I put it here. So it's hf over c. And then you say, ooh, hf, what's that? Oh, right, that's just going to be the energy of the photon. But here, it comes down to which version should we use? The one in electron volts or the one in joules, right? Part A didn't say which units to put it in, but only one of these will get you an answer that makes any sense. So if you didn't think it through, pause the video and think it through. Maybe you just intrinsically knew, but you have to think about this, right? Momentum deals with kilograms and meters and seconds, and C here, speed of light is going to be in meters and seconds, which means we can't be using electron volts. We have to use the one in joules, because a joule is a kilogram meter squared per second squared. So you have to make sure the units correlate, otherwise you're going to get an answer that won't have any physical meaning. So if you didn't do that, try it now. You should be using this value, the one that's in joules, and when you put the numbers in, we should be getting 1.58 times 10 to the negative 26th. I purposely left the units off because I want to see if you remember, of course, what unit should the momentum be in. Well, it's going to be kilogram meters per second, which, again, is weird because what's the mass of a photon? 0, right? It doesn't actually have mass. Even though it acts like a particle, it acts like a bit of matter, it's not. It actually has 0 mass, and yet the units in this are kilogram meters per second. It has the units of mass in it because those are the units of momentum. Before I move on, I just want to point out that we have another nice little relationship here. If we solve this equation, E photon over C equals P for E photon, we can rewrite this as E photon equals PC, which I'm going to ask you to box in as a new equation. You can put that in your notes. So now we have two different equations for the energy of a photon, one based on the frequency, the other based on its momentum. All right, on to number 8. So we've got a neutron with a de Broglie wavelength. So remember now, here's that other idea that de Broglie had. He said that if light, which is a wave, can act like a particle, maybe it goes the other way, that particles can act like waves. He postulated that, he got his PhD because of it, and then a couple years later, the guys Davis and Gurman, they proved it actually happens, and so we actually talk about the wavelength of matter, which is weird. Okay. So here we're going to use the equation lambda equals h over mv. Now, of course, this is the exact same thing as h over p. We could see that, right? But I really like to use this version of it because it has mass in it. So here again, we have the difference between a particle of light and a particle of mass. And since we know that we're talking about an actual physical object, I really like to highlight that by using the equation that has m in it. And remember, to remind ourselves that it is an object with mass. So we can just solve this for v equals h over m lambda. But its wavelength has to match the wavelength of the photon. We're given the wavelength of the photon, then maybe back in number 7 you found the wavelength, you just put it in, or maybe you want to do that. But I'm just going to replace lambda with c over f again, right? So the f goes to the top, c stays on the bottom. Why is this useful? Well, once again, we have hf on top, and hf is, again, the energy of the photon, right? So we can just write this e photon over mc. That's nice. But I wondered, did maybe do it a different way? Because there is another way to do this, maybe a little more sophisticated, clever way. Because we know its wavelength is going to match the exact same wavelength as the photon back in problem 7. And the wavelength is based on the momentum. So if we just use this equation, if it has the same wavelength, it has to have the same momentum, and we already know the momentum of the light, so it means it has to be the same momentum of the neutron. So we can just write P equals mv. and solve for V as P over M, right? You can just do that. There's nothing wrong with that, and you'll get very similar results regardless. Again, I think there's a little more sophisticated, a little more clever way of doing it, but the numbers are going to be pretty much the same. From here on out, it depends on which value of mass you use, whether you use the 1.67 or 1.675, which, we have a 4 sig fig version, so we might get a slight different range of values. So if you use this, you'll get 9.43 meters per second. However, with different combinations of the equations or different combinations of the mass, you might get 9.45, 9.48, 9.46. As long as you're getting one of those, you're doing everything just fine. Okay, so again, you send a neutron through a tiny, tiny opening, and it will act as if it's a wave. At this speed, it will have a wavelength that will match the wavelength of this photon, and it will, if there's a whole stream of them, they'll diffract and they'll form an interference pattern on the other side. So it leads to the question of why don't we just see that all the time? Well, we're talking about neutrons. These are ridiculously tiny objects. We can't see the neutrons, right? So we're not used to understanding what that looks like. But based on this equation, lambda equals h over mv, this means that every single object has its own wavelength. Now, if you did actually calculate the wavelength for the neutron in the previous problem, you'll find it's about 41.9 nanometers, or 4.19 to the negative 8 meters. If you think way back to when we were dealing with waves, we were looking at the size of the opening and how that affected the diffraction. And what we actually found was that the size of the opening should be about the same as the size of the wavelength to observe diffraction, which means that if a neutron were to exhibit diffraction, it would have to go through an opening on the order of nanometers, on the order of 10 to the negative 8 meters or so, and only then would you actually be able to see it actually diffract. For comparison, when we did the laser light shining on the hair, we all found something around 10 to the negative 5th, 10 to the negative 4th meters, right? So we're talking about a size of an opening that's ridiculously small, and that's what Davis and Gerber used. They used the size of the opening between layers of crystals, which were really, really tiny in width. You're not going to see this happen in everyday life. Then you say, well, you're an object and you move, right? That means you're going to have a wavelength. Let's say you're an object with a mass of 60 kilograms. Let's say you're just sort of walking along at 1 meter per second. We'll just do a quick calculation, right? We're going to use this equation here. Let's find your wavelength. Now just be careful which value of h should we use. Is it the 6.63 or the 4.14? Okay, hopefully you recognize it's going to be the 6.63 since we're dealing with kilograms and meters per second. That's the one that involves joules, which is related to kilograms, meters, and seconds. So let's just do a quick calculation here. 1 sig fig should be fine. Let's find your wavelength. Okay, so here's you walking through an opening, and your wavelength should be about 1 times 10 to the negative 35th meters. Good? Well, okay. We did just say that to observe diffraction, the object's wavelength should be about the same size as the opening, which means that if you, a mass of 60 kilograms, moving at this walking speed of 1 meter per second, want to diffract this opening has to be on the order of 10 to the negative 5th meters, maybe just a little bit larger than that. You're not squeezing through that. There's no way you could ever do that. So that's one good reason why you are not going to see you diffract as you go through an opening, like a doorway. So you say, well, wait a second. Let's say the doorway has a width of 1 meter, which means that if you could have a wavelength on the order of about 1 meter, you should observe diffraction for you. So again, let's assume you have a mass of 60 kilograms, and let's find how fast you should be moving to have a wavelength of 1 meter. So we can use this equation and calculate, again, 1 sig fig should be fine, your speed. Well, it's pretty much the same numbers as before, which means that you should be moving at 1 times 10 to the negative 35th meters per second. Sound good? What's the problem? Oh, that's very slow, you say, right? Well, let's just get a handle on exactly how slow that is. Let's say to cross the threshold of this doorway, the distance is about half a meter. Just, order of magnitude here, right? So let's go ahead and calculate the time it would take for you to traverse half a meter of distance moving at this speed, right? So t equals v bar t. Let's assume this is an average speed. Solve it for the time. And you should get a time of 5 times 10 to the 34 seconds, okay? So it's going to take you that long to go through this opening at this speed, in which case you should diffract because your wavelength is about the same size as the opening. What's the problem with that? Oh, it's a little bit long, you say? Well, let's look at a comparison here. Just for comparison, the age of the universe is about 10 to the 17th seconds. Yeah, okay. So it would take you longer than about the square of the age of the universe to go through that opening at this speed to observe you diffracting. That's why you don't notice yourself diffracting as you go through openings like doorways and things like that, right? Now, even if you did, though, what would you observe? If you went through this opening and diffracted, well, then you would expand, right? I guess that's what would happen, because that's what diffraction is. And if there were a stream of you, a whole bunch of 60-kilogram people all traveling around this speed and taking the time square of the age of the universe, then we would see an interference pattern of you on a screen over here. Yeah, and that's why we don't notice these things in everyday life.